Today I'm planning to do linear functionals. So what is a linear functional? So suppose f is a function from a vector space V. My voice is coming to me. Okay, now it is fine. So suppose V is a vector space. And the field for vector space is F. And if you take a function from V to F, and this function is linear, then this kind of function called linear functional. Okay, now let's take some example. So suppose f is a function from R2 to R, and this is defined as f of x comma y as x plus y. So you can check this is a linear functional. Okay, now if you take some other example, suppose f is a function from C01. C01 means the space of all continuous functions on closed interval 01. If you take this function R, and this function is defined as f of phi is any continuous function on closed interval 01, then define this function as 01 f of x dx. Now this function is well defined because every continuous function is integrable. Okay, so this is, and you can check this is a linear functional. And one more function you can take f of C01 to R, and the function you define as f of phi is equals to phi of 0. This is also a linear functional. Okay, now suppose this is actually standard notation. This is the space of the collection of all linear functional on V. This is either denoted by V star or sometime we denote it by VH. Both are the notations of this collection. Now you can check that 0 is always there. 0 functional is always belongs to V star. Okay, now if you take any f1 and f2 belongs to V star, then you can define addition as f1 plus f2 at point x is defined as f1 of x plus f2 of x. This is for all x belongs to V. Similarly, you can define alpha dot f1 of x is as alpha f1 of x. Okay, this is for every scalar. So you can verify that with respect to these vector addition and scalar multiplication, V star forms a vector space. Okay, now suppose dimension of V is finite, and to be precise, suppose dimension of V is n. Now what will be the dimension of V star? Okay. Now, suppose dimension of V is n, and the basis is x1, x2, xn. This is a basis for V, right? Now, if you take any member from V, then you can write this member x as summation alpha I I equals to 1 to n, right? Because B spans V. Okay. Now, if you define your function f1 as f1 of x is equals to f1 of summation alpha I equals to 1 to n as alpha 1, the first part, the first scalar, then you can prove that this is a linear functional. Now, similarly, for j belongs to 1 to n, if you define fj of x as fj of summation alpha I is equals to 1 to n as alpha, the jth entry, alpha j, then you can prove that this is also a linear functional. Now, what can you say about this set? Is it linearly independent or dependent? This is the question. Now, suppose you take any linear combination of this functions j equals to 1 to n, and suppose this linear combination is equals to 0. Okay, what is the meaning of this? The meaning of this is summation j equals to 1 to n lambda j fj of x equals to 0 for all x belongs to V, right? Now, if you take your x equals to x1, then summation this lambda j of fj at x1 j equals to 1 to n will be equals to, for f2 x1 it is 0, f2 f3 x1 it is 0, like this fn x1 equals to 0, and f1 x1 is 1. So this is equals to lambda 1, and this is equals to 0, so lambda 1 equals to 0. Similarly, you can prove that if you take this summation lambda j f j at point xi, then it will be lambda I, and this is equals to 0. So this shows all lambda I are 0. So the meaning of this is the set A is linearly independent. Okay. Now, suppose you take any f belongs to V star. Okay. Then, and take lambda I equals to f of xi. Okay. So if you define your h as summation lambda I f of, so we have already taken I, so you should write j j equals to 1 to n, then you can prove that this h is nothing but your f. So this f belongs to span of A. So what we have just proved, so this set A f j varies from 1 to n is a Base is for V star. Now tell me what is the dimension of V star then?
V, the dimension of V.
Yeah. And what is the dimension of V?
N. N.
Mm, yeah.
N. Okay.
Okay.
Now, now let me tell you some properties of this function. Suppose f is non-zero. Non-zero means so there is one member x in V such that f of x is not equals to 0. Okay. Now what can you say about the rank of this f? What will be and here we are taking dimension of V as n. Even you don't need this one also. What can you say about the rank of f? So rank is just the dimension of range space of f, right? And the range space of f is a subspace of codomain vector space. Now here f is a functional, so it is a function from V to R. So this is a subspace of R, right? Now what is the
And
dimension
it
of
is
R?
the dimension of R is one. What?
Yeah, dimension of R is 1. So dimension of
Mm.
this range space can be either 0 or 1, right? Because the dimension of the bigger space is 1.
Hello, sir.
Now we have taken that this f is non-zero functional.
Sir, sound is not coming, I think.
Okay, now am I audible? Hello,
Yes, sir.
am I audible?
Yes, sir. You are audible.
Okay, so now so dimension of range space of f can be either 0 or 1, right? Now but we have taken that f is non-zero, right? So this range space is not 0. At least this vector is there. This vector is belongs to the range space of f. Okay, I should say this vector y, f of x. This y belongs to this r of range of f, and this is not 0. So the dimension cannot be 0. So the only remaining option is dimension is 1. So the rank of a non-zero linear functional is always equals to 1. Okay. Now if dimension of V till here we don't need dimension finite dimensional. Now suppose I'm taking dimension of V is n. Now can you tell me what is the nullity of f? What is the nullity of f? Use ring nullity theorem.
N minus 1.
Yeah, it is n minus 1 because the rank of f plus nullity of f equals to dimension of V, and the dimension of V is n. So the nullity of f will be n minus 1 for every non-zero functional f. Okay, even I can tell you one more property. Suppose f is non-zero linear functional, then you can always write your vector space V as the, the null space of f. Okay, we don't need the finite dimensional here. Dimension of V can be anything. Okay, now suppose this is non-zero, so there exists some x such that f of x equals not equals to 0. Okay, so if you have this situation, then v can be written as null space of f direct sum span of this member x. What is the property of x here? F of x not equals to 0. You take any x. You take any.
Sir, repeat once. I have not understood what is this.
Okay, let me repeat this again. Suppose f is any non-zero linear functional. Okay,
Okay.
from v to f. Okay, now since this is non-zero, you can have one x such that f of x not equals to 0. Now you can always write your v as null space of f direct sum span of this vector. Now suppose you want to take some other y such that fy not equals to 0, then you can always write v as null space of f direct sum span of this y. Now how will you write this? Now suppose take any member. Suppose we have already used x and y, so we can take z. Suppose z is a member in v. Okay, so since let's prove the first one. So f of x is not equals to 0. Okay, now take alpha as f of z divided by f of x. We can do this because f of x is a scalar.
Scalar, yes.
Okay, and we can do because f of x is non-zero, we can divide f of z by f of x. Now this is a scalar. Okay, now can't you write your z as okay? Can't you write your z as z minus f of this scalar alpha, then x plus alpha x. Now let me explain this. So of course, when you simplify this, you will get z because this alpha x and minus alpha x. Now only remaining is to show that this part actually belongs to null space of f. This is definitely belongs to span of x, right? The only remaining is show that this part belongs to null space of f. Now if you take f of z minus alpha x, it will be f of z minus alpha f of x. Now what is the value of alpha? So the value of alpha is f of z minus f of z divided by f of x into f of x. This two thing will get cancelled. Fz minus fz, it will be 0. So this member is actually a part of null space of f, and this is belongs to span of x. Now the same thing you can do if you take your beta as f of, now suppose z is your member. For this z you can define f of z divided by f of y. Now you can write your z as z minus beta y plus beta y. So this is definitely belongs to span of y, and this is belongs to null space of f. So you can always even, and you can verify this. What is the intersection of this? What is the intersection of null space of f intersection span of x? Okay, can you tell me quickly what is the intersection of those these two subspaces?
Zero element only.
Only zero element, right? Because If you take any member here, suppose W is any member in the span of in the intersection. Suppose W is any member in the intersection. So f of W will be 0, and W belongs to span of x, then W will be alpha time x. So f of W will be equals to alpha times f of x, right? F of W equals to 0, so 0 equals to alpha f of x. Now f of x is not 0, so the alpha has to be 0, so W has to be 0, right? Now after looking at this relation, can you tell me what is the codimension of null space of F?
It is 1.
Yeah, it is 1. So whatever non-zero functional you choose, the codimension of null space of 1, the null space of F will always be equals to 1. Okay. Now, so let me ask you one more question. Okay, suppose you have a function f from V to the field f. Now you have two and member x1 and x2. These two are linearly independent. Okay, and I'm saying f of x1 is not equals to 0, f of x2 not equals to 0, right? Now the question is, can f be linear? Okay, tell me, can f be linear? Am I audible?
Yes, yes, I'm thinking.
Okay, so can this f be linear? Because here you are saying the null v can be written as null space of f direct sum span of x, means
Yes.
only one point is there, like codimension is only one,
Hmm.
and here you are asking, do you have two linearly independent members, and on those members the value of f are non-zero.
It is not possible because one only f of x1 or x2 only not equal to 0, then it fulfills the criteria of
But I'm
what.
saying this is linearly independent. Zero is not
uh,
the x1 is not equals to 0, x2 is not equals to 0, x1 not equals to x2.
hmm. That is why in this way its
So the
code and
answer,
answer codimension of null space greater than 1 in this case. So is it be possible for
so the answer for this question is yes, it can be possible. Now let me explain why it can be possible. So you are saying y is equals to null space of f. The answer, it will may or may not be, like in it may possible that it is linear. Now let me explain why it can be linear. So you are writing this as direct sum span of x, okay, and here f of x is non-zero, right? Now suppose you take two member x1 and x2 which are linearly independent but also belongs to null space of f. Okay, now the value of x1 and x2, if you operate f on x1 and x2, you will get 0, right? Because belongs to null space of f. Now what will happen if I take x1 plus x and x2 plus x? Now if you operate f here, definitely it is not 0. If you operate f here, it is also not equals to 0. Now x1 plus x and x2 plus x, are these two member linearly independent? Because your x1 and x2 are linearly independent. So can you tell
yes, yes,
me? So definitely it will be linearly independent.
yeah.
So it doesn't mean you cannot have two members where value function cannot take non-zero values. It's the
See,
only meaning is you just add one more element in the null space of x where f of x is non-zero. If you do this thing, if you add this part, then you will recover your v. This is the only meaning. It doesn't mean two linearly independent member cannot have non-zero value.
And EPT is given that if this x1 x we are not choosing x1 x1 x2 which are not belongs to null space, then it cannot be possible. Okay.
So these two elements are not in null space.
Yeah. Here x1 and x2 belongs to null space, no?
But I am your question is, if it is given that both the members x1 and x2, like so let me write y1 and y2, if f of y1 is not equals to 0 and f of y2 not equals to 0, and both y1 and y2 not belong, of course they are not belongs to null space of f. Ah, your question should be, suppose you have this kind of situation, and if you write y1 is equals to,
Yeah.
so suppose because this, so y1 belongs to v, so you can write y1 as a member of null space. So suppose the z1 plus a member of, say, alpha 1 x, you can write
Mm,
this member as this one.
yeah.
Okay, and y2 you can write as z2 plus alpha 2 x. So definitely this part is linearly dependent always,
Yes.
but this part can be linearly independent. This part will always be linearly dependent, but this part can be linearly independent or linearly dependent.
Yes.
Okay, don't get confused with this thing.
Okay,
Okay,
sir.
now let me tell you some more properties. Now suppose you have a vector space V, okay, and W is any subspace of V, okay, and you have a linear functional G on W, okay. So this is, suppose this is a subspace and this is a linear functional on W, then you can always find a function f linear functional on V such that f and g are equal on W. So f of x equals to g of x for all x belongs to W. You can always extend your linear functional on a subspace to the whole space. Okay, this is one of the important property. You can always extend your linear functional from a subspace to the whole space. Okay, and let me tell you one more property. Now suppose you have some linear functionals, suppose f1, f2, fn. These are linear functionals, say a subset of v star. Okay, now suppose g is any linear functional which belongs to span of a. Okay, so if g belongs to span of a, then you can write g as summation of alpha I fi, right, because it belongs to span of a, right. Now if you take a member x in v such that fi x equals to 0 for all I equals to 1 to n, right. The meaning of this is x belongs to intersection of null space of all fi I equals to 1 to n. Now then what can you say about this g of x? What is the value of g of x? Okay, what is the value of g of x? Fi of x is equals to 0 for all I. Now what is the value of g of x? Hello?
Yes, sir, thinking. Uh,
See, fi of x is equals to 0 for all I.
yeah,
So it will be g of x will be summation alpha I
yeah,
fi of x. This is 0. So this is alpha I into 0. So it will be 0.
0, 0.
Yeah. So it is 0. So x belongs to null space of G. Okay. So you can, what you can say from here? So the intersection of null space of Fi, I equals to 1 to n, subset of null space of G. Correct? We have just proved this. We took one x from the intersection of null space of Fi, and then we proved that x is also belongs to null space of G. Now the question is, this is the only case this is the only case when G belongs to span of Fi's. The meaning is, let me write the precise statement. So G belongs to span of Fi if and only if this null space intersection is subset of null space of G. This is if and only if actually. And this is actually very strong statement, very important and strong statement. Okay, now let's move to the annihilator. Now suppose V is a vector space. Now suppose you take A is any subset of V. A is any subset of V. It may not be a subspace. Now A annihilator is defined as the collection of all linear functional such that f restricted to A is 0. Or the meaning of this is f of x is equals to 0 for all x belongs to A. Okay, or you can write this as A annihilator, A perp. Both are the notation for this one, but like I use this one. Okay, now suppose B is a subset of V star, and you define B annihilator as all the member of V such that f of x equals to 0 for all f belongs to B. This is actually intersection of f inverse of 0. I f belongs to B. So this B may not be a finite set. Okay. Now, can you tell me what is V perp? V annihilator? V is your vector space. Can you tell me what is V annihilator? Use this definition.
Null space,
Yeah,
null space of,
it will be the zero, zero, zero functional.
yes, sir.
Hello, am I audible to you?
Yes, now audible.
Okay. Now, so this V annihilator will be the zero function only. Now, similarly, if you take the whole V star, what will be the V star annihilator? This is zero functional, and this will be only zero vector with zero member. Okay. Now, let me take some example. Suppose your set F is your set A, your vector space is R2, and your set A is singleton F, and your F is defined as x comma 0 is equals to x comma y is equals to x. Okay. Now, can you tell me what is the annihilator of A? This will be just null space of F because only one element is there.
Yes,
Okay.
so
And
y-axis is it.
it is with y-axis, or you can write this as x comma 0 comma y. Y belongs to R. Okay. Now, if you take two member, say F1, F2 in R2, and your F1 is defined as y is defined as x, and F2 defined as y. So what will be the annihilator? What will be the annihilator of?
It is 0, 0 only.
Hello?
Hello.
Hello? Yeah.
Yes.
Okay. So what is the annihilator of A?
It is 0,
One
0 only.
intersection null space of F2. Right? So I did this spaces, null space of F, F belongs, right? Now, in this case, we have only two members. So it will be intersection of null space of F, null space of F2. Now, what is the null space of F? So what is the null space of F1? Here, the null space is y-axis, correct?
Yes.
Okay, this is y-axis. Now, what is the null space of F2?
X-axis.
X-axis. Now, what is the intersection?
0.
So this is 0. Now, okay, let me write one more property. Then we will do something interesting. Okay, so if A is any subset of V star, then A may not be a subspace. Okay, then A annihilator is always equals to span of A to the annihilator. Now this is a subspace. Okay, this is a subspace, but this is not a subspace. Even if you take, okay, let me write here. If you take any A subset of V star, then A annihilator will always form a subspace of V. And if you take A subset of B subset of V, then B annihilator will always form a subspace of V star. Okay, and the question is, even it is very easy to verify that A is, in this case, A is always subset of, now you take A annihilator, now it is a subset of V star, and you take the reverse annihilator. Similarly, in this case, B is subset of B annihilator, and you take reverse annihilator. Okay, now the question is, when A is equals to A annihilator, reverse annihilator, when B is equals to B annihilator, annihilator. Now this is always a subspace. This is always a subspace. So these two will hold if and only if A and B are, A is a subspace of V, B is a subspace of V star. For subspaces, these two property always hold. Okay. Now, now suppose you have any subspace W of V. Now, what can you say about that? Okay, let me take the subspace of V star. Now, suppose Y is any subspace of V star. V star is a subspace, is a vector space. Okay, suppose this is a subspace. Okay, so we are doing this. Now let's come back to the example. Okay, now take span of A. Here A is the singleton F. Okay, now take span of A. So this is a subspace, and this annihilator is equals to A annihilator. Okay, now what is the dimension of A annihilator? What is the dimension of A annihilator? What is the dimension of Y axis?
1.
1. Okay, now similarly, in this case, what is the dimension of, okay, this, if you can check that this, and in this case, what is the dimension of this space? This is only one dimensional because it is span of F. The dimension of this space is 1. A annihilator is also 1. Now in this case, what is the dimension? These two linear functions are linearly independent. You can prove this. Okay. Now what is the dimension of this span of A? Because these two elements are linearly independent, so the dimension is 2. Correct. Now what is the dimension of this span of A annihilator? This is only 0. Right, so dimension is 0. Right. Now can you see some relation here? Dimension is 1, dimension is 1. So what is 1 plus 1? 2, and 2 is the dimension of domain space. Now here 2 plus 0, dimension of domain space. So are then dimension of y plus dimension of y annihilator is always equals to dimension of v star, or this is actually equals to dimension of v. Similarly, if W is any subspace of V, then dimension plus dimension of W annihilator is always equals to dimension of V, and this is equals to dimension of V star. Okay, so these are two important properties. Okay, let me ask you one more question. Now suppose you have two subspaces W1, W2, subspaces of V. Okay, and I'm saying W1 is equals to W2. So what can you say about W annihilator and W2 annihilator?
They must be equal.
They will be equal. Okay. Now the question is, suppose you have two subspaces W1, W2. These are subspaces, and you know W1 annihilator is equals to W2 annihilator. Then what can you say about W1, W2? So the answer is they will always be equal. So this is if and only if. Okay. For more information of annihilator, about annihilator, you can read on Kunje book. Okay. And let me tell you something about eigenvalues. I think you are it is the first time you are doing annihilators. So yeah, let me do something on eigenvalues. Okay. Now suppose you have a linear operator. Whenever you say a linear operator, that means the domain linear transformation plus domain and codomain space are same. So this is called linear operator. Okay. And we say lambda from field is an eigenvalue for this t if tx equals to lambda x for some 0. Okay. So from this, if suppose lambda is an lambda for a linear operator t, then what can you say about the nullity of t minus lambda I? The null space of t minus lambda I, it will never be equals to 0. Even this is if and only if. Okay. And if you I think you know about this, every linear transformation can be represented as a matrix. Okay, this is the matrix representation of linear transformation. Suppose your linear transformation from V to W, and this is dimension of this is n, dimension of this is m. Then the associated the matrix representation, the matrix will be of the order m cross n. Now in this case, what we have T from V to V, and suppose dimension of V is n. So the associated matrix will be n cross n matrix. So that's why it is enough to study eigenvalues for a square matrix. Okay, so lambda is an eigenvalue for a matrix A, square matrix A, n cross n, is valid if Ax equals to lambda x for some non-zero x. Okay, and this is valid if and only if the nullity of A minus lambda I is not equals to 0. This is if and only if the rank of A minus lambda I is not equals to n. This is if and only if determinant of A minus lambda I is equals to 0. This is if and only if, so what is remaining, this A minus lambda I is not invertible. So all these statements are equivalent. Okay, now the question is, actually I want to do one question, so that's why I'm doing eigenvalues. So the question is, suppose you collect all the eigenvalues, okay, this, suppose okay, in this case this x is called eigenvector. Okay, and the matrix case also this x is called eigenvector. Okay, now the question is, suppose you consider W is the collection of all eigenvector corresponding to an eigenvalue lambda. Now the question is it a subspace? Is it a subspace?
No, set of eigenvector is not a subspace because they are non-zero. Eigenvector are always non-zero.
Yes.
And
Answer is no, it is not a subspace. The reason is 0 does not belongs to W. Now suppose we add 0 in W. Then what can you say about this one?
it is a subspace.
So it is a subspace. Now it will form a subspace, and this space is called eigenspace. Okay, now the question I want to ask is, like, suppose you have a n cross n matrix. Okay, now how will you find the eigenvalue for A? You know that if lambda is an eigenvalue for A, then determinant of A minus lambda I is 0. Okay, you just calculate this polynomial P lambda is equals to A minus lambda I, determinant of A minus lambda I. Now find the root of this polynomial, and you will, that will be your eigenvalues. If your field is complex, then by fundamental theorem of algebra, this polynomial, the degree of this polynomial will be n. Now if your field is complex number, then this polynomial is a polynomial of degree n. So this polynomial have exactly n roots. So you will have exactly n eigenvalues. Okay. So in finite dimensional, so this is your n cross n matrix, of course finite dimensional. In finite dimensional, you will always have eigenvalues corresponding to a matrix or a linear transformation. So every matrix is a linear transformation, every linear transformation is a matrix. Okay. So in finite dimensional, if your field is complex, then you can always find eigenvalues for that corresponding to that matrix. Even you can, if your matrix is n cross n, then you will have exactly n eigenvalues that corresponding to that n cross n matrix. But you may not have real eigenvalues. For example, if you take a equals to 0 1 1 0, yeah, then you will not have any real eigenvalue for this matrix, because the characteristic polynomial, this polynomial is called characteristic polynomial. So this characteristic polynomial for this matrix square minus 1. If you put this equals to 0, then you will get lambda equals to plus minus iota. Although all the entries are real, but you don't have any real eigenvalue here. Okay, now the question I wanted to ask is, now suppose you have a linear transformation from V to V, and the dimension of V is not finite. So does T have any eigenvalue? The meaning of an eigenvalue is there exists some lambda and x non-zero such that Tx equals to lambda x. Okay. Now dimension of V is not finite. In finite dimensional V, even the field is complex. So eigenvalues corresponding to linear transformation or matrix. But the question I want to ask is, if suppose your dimension is not finite and your linear transformation is from V to V and your field is also complex. Now, does T have any eigenvalue? Okay, what is your answer?
It may be, may not be.
Okay, can you tell me any example? If you are saying it may not be, then you should have any example for that. Okay, what about this linear transformation? C01 to C01. And I am taking this linear transformation as P of f is equals to x. X is a continuous function, f is a continuous function, the product of two continuous function is continuous, so this is also a continuous function. So this is well defined. Okay, and you can check that this is linear also, because if you take f1 plus f2 and if you multiply this x, and you will get x f1 plus x f2, right? Similarly, you can manage the scalar multiplication. So this is linear. Okay, now the question is, does T have any eigenvalue? Okay, suppose T have an eigenvalue, say lambda. Okay, now lambda can be a complex number, so write this lambda as lambda 1 plus iota lambda 2. Okay. Now, since our field is complex, so if you have any continuous function, your continuous function will be of the form f1 plus iota f2. Okay, they can take complex values. Now, suppose t of f is equals to lambda of f, and we are taking f is non-zero. This means f of x is non-zero for some x belongs to close interval 0, 1. Okay. Now, what is the value of this? This is lambda 1 plus iota lambda 2. What is the value of f? f1 plus iota f2. So this is equals to this one. Now, what is the value of t of x into f? 1 plus iota f2. So this will be x f1 plus iota x f2. Okay. Now simplify this term. What you will get? Lambda 1 f1 minus lambda 2 f2 plus iota lambda 2 f1 plus lambda 1 f2. Correct? Right. Now this is the real part, this is the complex part, and these two things are equal. So this lambda 1 f1 minus lambda 2 f2 will be equals to x into f1. Right. Similarly, this lambda 2 f1 plus lambda 1 f2 is equals to x into f2. Right? Compare the real and complex part. Okay. Okay. Now what can we can do here? Now compare these two equations. In this side we have f1. In this side we have f2. Now multiply this equation by f2. Multiply this equation by f1. Then what you will get? Lambda 1 f1 minus lambda 2 f2 square is equals to lambda 2 f1 square plus lambda 1 f1 f2. Right? Now what can you say about this part and this part? They are same. So lambda 2 f2 square is equals to lambda 2 f1 square. This is minus. Okay. Now what will happen? Lambda 2 f1 square plus square is equals to 0. Now from this what you will get? Either lambda 2 is equals to 0 or both f1 is equals to 0 and f2 equals to 0. Right? Otherwise this cannot be equals to 0. Right? Now this cannot be possible because otherwise this f will be 0. lambda 2 equals to 0. Okay. Now similarly, you can, if you multiply in this equation by f1, and here if you multiply by f2, if you simplify that, you will get lambda 1 equals to 0. So the eigenvalue lambda is equals to 0. So 0 is the only possible case. Now, so T of f is equals to lambda of f. Now what is the value of T of f? X into f is equals to lambda f. Now f x minus lambda is equals to 0. Okay, I should write x minus lambda 0. Right. Now, as I said, f is not equals to 0. That means for some point, say x naught, this is not equals to 0. If you put that point x naught, what you will get, lambda is equals to x naught. Okay. So from this point, what you will get, this point x naught has to be 0. Now this is a continuous function, and you are saying at around x naught, this is not 0. This is 0. So you can find any other point z in neighborhood of this x naught, such that fz is also equals to 0 and x naught is not equals to z. But that cannot be possible. Lambda cannot be equals to x naught. Contradiction. It is actually not an easy observation, but the point is, if your dimension is not finite, then the linear transformation may not have any eigenvalue. And the example for that, you can take this one. You just take T linear transformation from C01 to C01, and the transformation is T of f equals to x into f. Then this linear transformation cannot have any. Okay, and this is one of the important example. Okay, with this, let me stop here. If you have any question, you can ask me. Am I audible?
Yes, sir.
Yes, sir.
Okay. Do you have any question?
No, from my end.
Okay. If you have any question, you can send your question to me through email. And if you don't have any questions, so let me stop here. So, okay. Best of luck for your exams. Thank you for attending this session.
Thank you, sir.
Thank you, sir.